Thank you. My name is Rani. I'm a security researcher. I'm really excited to be here at in the Box Singapore. Today I will speak about the road to iOS Sandbox Escape. My main goal is to deliver you guys how iOS is exactly like any other platform, closed source platform, of course, in the aspect of research, and my results with my first research I conducted over iOS. So I actually started with really lack of experience in the iOS field. So what I did was just starting to read a book and go ahead. So what are we going to cover today? We will cover briefly short introduction to iOS, some terms we need to make sure we all know. iOS containerization, also known as the sandbox. We'll a little bit talk about deal shared cache. We'll speak about launchd and mach messages, which are important for the research I conducted, and basically for any research you will probably have on iOS. And we will go and dive into the two approaches ahead for finding Sandbox Escape. We will understand what is Sandbox Escape and whether it's going to be ETA soon from those vulnerabilities, because this is the most important part for some people. And if we will have time, I think we will, we'll have questions. So who am I in more detail? Security researcher. I'm director of platforms research at Zimperium Z-Labs team. I based in Tel Aviv right now, in Israel, and I'm an iOS researcher. The difference for me is that this is really a new field for me. I never did anything with mobile platforms, so iOS was the first time. So, what is iOS? The overall terms we need to know, it was evolved from OS 6 and is based upon the Darwin operating system. In many ways, it is similar to all of the other OS devices, tvOS, macOS, watchOS, but is slightly different in many aspects. It is built upon the XNU kernel, which is basically open sourced, and it is strictly enforces the notorious sandbox. That means there is the notorious jail, and from the jail community, there is the jailbreak process, which basically gives you a read and write. You know, the jailbreak means that you will have full execute and write over the system partition. It is done in many different ways, and this is not the case of my talk today. I will cover only the Sandbox Escape aspect. So basically on the design of the operating system, and again this is only a redundant image of the operating system, you can roughly divide it into three parts. You have the application, the core services, I will also call it brokers, and the kernel. And let's take YouTube for an example. All of the application side basically means the untrusted code by the operating system, which is being executed under really restricted sandbox limitations. So whenever YouTube wishes to decode a frame it got of, I don't know, some funny cat video, it will use the video toolbox, the video toolbox API, and will ask for mediaserverd to communicate with the kernel in order to decode that frame using IOKit communication. So this is roughly the sandbox design, because each application will be able to communicate with the corresponding daemon only if it needs to. That means that if, for example, Safari doesn't need Bluetooth, which is not true, it will not be able to communicate with Bluetooth, and definitely will not be able to communicate to the kernel extension that handling the Bluetooth communication. Sorry. So this is the main design of the operating system. And now, in order to improve some performance, Apple decided to combine all of the system libraries and to put them into one file, which is known as shared cache. Basically, it is some kind of similar to kernel 32DLL, not the same, but similar. There are several ways to analyze it. You can use IDA, you can use JTool, you can use a lot of different open source tools you can find online on GitHub. Personally, I used only JTool and IDA, and we will understand in a few slides why it is a huge challenge for iOS researcher. I think another speaker talked about it just today. So, IPC, the IPC in iOS, Apple decided to implement different IPCs on different layers that are all kind of built upon mach messages. Most of Apple IPCs are based upon the mach messages. This is why it's really important to understand how mach messaging is working. Apple also decided to to implement some of the regular POSIX IPC. So let's dive into mach messages. Basically, like I already said, this is the underlying IPC underneath of most of all the others, like XPC or distributed objects. It is used within the kernel and the user mode, and it's also, of course, used to communicate with the kernel. Mach message trap is the syscall that is being used to send mach messages, and one of the parameters to mach message trap is distract. Distract basically means we'll cover some of the fields here. The message bits used to set the type of the message. The sender of the message can specify if the message is complex. If the message is complex, there is going to be added the actual data after the header, and the size of the data is going to be defined by the message size. There is also the field of the remote port that is used to specify the destination of the message, the port of the message, and the local port, which is actually an auxiliary port. You don't have to specify the local port. This is telling to the recipient where to reply the message. And there is the message ID, which basically used to convey the function ID of the message. That means, again, it's only conventionally used. It is used to tell the recipient which message to invoke. Which callback to invoke, but we have some kind of a problem, because how do I resolve that remote port if I'm an application? How can I know how to communicate with mediaserverd, for example? So Apple implemented it using LaunchD. LaunchD is essentially, you can have a whole talk only about LaunchD, but if we want to redundant it, LaunchD is kind of the mother or the father of all the other user mode daemons or processes. It is used to stop and start daemons, application and processes on demand. You can think of it as the supervisor on the user mode side. And it is also used to resolve daemons. So whenever a daemon, let's for example process A, wishes to register as a new mach server, it is going to use the function bootstrap check-in and will ask LaunchD to hold the handle to this port and using the name. The name for our example is com.new.demo. Afterwards, LaunchD will hold that the port process A send him, that it will be attached to that name. So when process B will want to resolve the new mach server, it is going to use bootstrap lookup and ask from LaunchD that port. LaunchD will reply him with the port that it can, from that moment on, can use in order to communicate directly from process A to process B. So let's dive a little into some of the iOS research difficulties ahead. And basically, any other researcher is coming across those difficulties. First of all, the device is jailed. That means you cannot really execute your own code outside of the sandbox limitations unless you are using some vulnerability that is out there. And on every new version, there is one popping out. You cannot really attach debug to daemons. What I mean by that is that when you already have a vulnerability, you cannot really debug it in order to easily or comfortably exploit that vulnerability. So you need to rely on the crash reports from crashes you have, or the device console, which basically means the logs of the device. And moreover, you cannot really flash old versions. That is why you will see a lot of iOS researchers desk bunch of different devices that you need to gather around. And by insufficient documentation, I mean that Apple does not really document anything that is not for the developer. That means you will not find information that is not relevant to the SDK. Of course, there are a few exceptions, but basically it means that you cannot really know how they implement a lot of stuff within the operating system. And IDA really struggles with the dilshared cache that we mentioned before in the previous slides. So what you have to do is basically get a workstation with a lot of RAM sticks and hope that it will finally be able to analyze dilshared cache. So while I was also working on some IDA Python scripts to improve that with IDA, they released IDA 7, which actually got you the ability to load one image with all of its dependencies, and you will not need to load a 1 gigabyte of code, which basically means it kind of solved the issue of dilshared cache, but still it's not really a good idea to try to extract some functions. It will probably just crash because there are thousands of functions within dilshared cache. So, what is a Sandbox Escape actually? Basically, let's assume we are a malicious application and we want to get to the kernel eventually. But right now, within the sandbox, our attack surface is really limited. We can contact only the daemons we can use, or we can access only few of the kernel features. But if we will be able to exploit or get arbitrary code execution over one of the daemons, we will be able to widen our attack surface, and for mediaserverd, we will be able to widen our attack surface, and eventually we'll get to the kernel by different vulnerability. Now, I think it's worth to mention that when you're choosing which daemon is your target, you should search for the one with the widest attack surface. That means wifid will probably, not really, but probably will be able to communicate only with the Wi-Fi drivers, but will not be able to communicate with other Bluetooth drivers, for example. That's why we will see it later that wifid is also a client of Blue2D. It cannot communicate directly with the Bluetooth drivers, which makes sense because you need one daemon to manage the Bluetooth stack. So I started to choose my target. I used SBTool by Jonathan Levin. Basically, it inspects the sandbox profile, and obviously you can run an SBTool only on jailbroken device. And yet it helps to get a feeling of the operating system to start and search for your next daemon target. In our case, I choose, not really arbitrarily choose, but randomly choose, let's call it, to focus on those two mach servers. Again, these are the name of the mach server that daemons were registering as new mach server using Bootstrap Lookup. The first one is the Apple Core Media Decompression session that is being handled by mediaserverd, and there is Apple Server Bluetooth, which is being handled by Blue2D. All you have to do, just take the string, basically, go to the shared cache, and find the right string for that mach server, and find where the mediaserverd registers as a new daemon, as a new mach server. This is the function that it's using to register as a new daemon. It's fig_rpc start server, which is getting a few different parameters, but the first parameter is the name of the new mach server, and the third parameter is function that handles each mach message that is being received. Let's dive into that handler. That handler is pretty simple. It has the in and out message pointed to the input mach message and to the output mach message. It is going to use the message ID, decrement some constant number that is being changed by each mach server, as far as I see, as I found out. It is going to check if that message ID, which again is used to convey which logic needs to be invoked, and it's going to check the message ID that it's below or equal the number of how many callbacks there are. Going to retrieve the address of the callback by using the VTD compression subsystem struct, and eventually it's going to call the handler with the input and output message. Now, all I had to do is to go to that struct and to understand which callbacks I can invoke. So I found out that this struct holds different, this is only a short list of all the callbacks. I found that I have xcreate, xstore, and xDecodeFrame. Again, each callback is, let's recap a little. Each callback is invoked by the message ID from our sandbox application. That means we can call to each one of those callbacks. So I decided to dive into the xDecodeFrame, because this is the main logic of the decompression session, as you might guess. And the xDecodeFrame, after a few research and actually checking the API and seeing what is calling the xDecodeFrame, I found out that it's the backend of the API called VTD compression session decode frame. It is decoding frame from a serialized buffer. What that means that whenever application wishes to decode frame, it is going to serialize the request. We will see how it's serializing in a moment. It is going to send that serialized frame, serialized sample buffer to mediaserverd. Mediaserverd is going to deserialize it and to sending it eventually to the kernel in order to decode the frame. Eventually, it's going to return a message with the result code back to the client. So what we can see about the logic of decode frame is pretty obvious. It is going to find the session, the corresponding session by the local port. That means by who sent that message to mediaserverd. This code is being executed on the mediaserverd. And eventually it's going to call create sample buffer from serialized atom data that is going to deserialize the request. So I stopped for a moment, and again, remember it. This is the first time I'm doing anything on iOS, and I decided to doing something I'm not doing every time, which is to manual analysis the deserialization process, intercept legitimate, in order to understand the deserialization, intercept legitimate buffers, legitimate serialized buffers, and eventually modifies those buffers. Basically, it shouldn't be profited, it should be called fuzzing. And I wanted to gain out of it really a lot of, just to get a feeling, what I'm doing here. So let's understand what is actually happening whenever there is a decompression session. One application, again, I like to take the example of YouTube, want to decode the new frames it got from the internet. It is going to set up a new decompression session. It is going to send a mach message with the information about the new session to mediaserverd. Mediaserverd is going to handle that request by the callback xCreate we just saw. And eventually it is going to call the API called with the decompression session, the coldframe. And the application is going to serialize the request in order to send it, again, using mach message to the callback xDecode frame by mediaserverd. So we have a really nice attack surface here because this serialization process is known as sometimes as difficult to develop properly. So I had to understand a little bit what is this serialization process. And the serialize is actually a really obvious one. It is called create sample buffer from serialized atom data and surface, and it is actually just a TLV, a type length value. In that case, it was a length type value, but it's the same. Each node is actually 4 bytes that are describing the size of the next of the node, 4 bytes that are the type of the node. The first root node is always SBUF, sample buffer, actually. And then you can have nested nodes that are holding different information of the frame you want to decode. So I implemented it real quick on Python. It's just regular TLV. The reason I did it was to being able to send raw serialized buffer to mediaserverd without going through the legitimate API. In this way, I could bypass a lot of the checking on the side of the application. And eventually, I wanted to create a sandbox application that I will be able to file mediaserverd. So let's see. What I did was taking a legitimate application, asking it to decode frame, intercepting the frames, the serialized frame, already the serialized frame, and while working raw on that serialized buffer, I chose to modify those buffers on interesting places. Of course, not on the type of the node, because I want to bypass those checks, but basically on the size of the node or the actual data. And eventually going to replay it back to xDecode frame. In this way, I managed to generate, 700 megabytes of different, unique, serialized corrupted buffers. And to see what's going on. So I let it to run for, I think, few hours. And, well, the results were just huge. I was being able to create about 3,000 crashes on mediaserverd. And after going through those crashes, I found out that there are 31 unique crashes, which is still a lot. After going through those crashes manually and writing some scripts for those, I found out that the bugs, still not vulnerabilities, are some stray asserts Apple forgathered from probably debug sessions, some null dereference, and some more interesting bugs, like use after free, out of bounds read, and out of bounds write. Sorry. So while I was traveling to DEF CON and Black Hat, I think it was last year, I was really thrilled about it. I wanted to go back and see what I have in my hands. And what happened next was the most obvious for any iOS researcher, iOS 11. And as long as they decided to implement new important stuff like document scanning or iPad multitasking, trying to do it again, they also decided to refactor mediaserverd. So I tried it again, all of my new corrupted buffers, but no, it didn't work. It stopped working. So I could decide whether I want to do it again. Maybe I missed something. Maybe I'm not using the API call correctly. But what I had in mind, if this is what I could achieve on my first try, I can do it again. Let's do it with Blue2D. Blue2D, just to give you some terms, it was rebranded from mediaserverd. It is implementing the Bluetooth stack on the user mode, and it actually centralized all the Bluetooth communication on Blue2D. And each process with Bluetooth entitlement will communicate using Blue2D. That means it will not be able to communicate directly to the kernel. In our terms, this is a trusted broker, and a lot of other daemons and applications are using Blue2D. So it's really interesting way to widen our attack surface. So I did all of what I did in mediaserverd, understanding the callbacks, finding out where is the code is exactly being executed, and I found this callback, which is called getPairDevices. And again, we have the in and out message. This time it looks much better because I implemented some IDA Python script that is taking all the mach arguments from a legitimate from the daemon and reflecting it back to IDA. Therefore, I will be able to have the correct struct sizes, and maybe I will be able to automatically fill those fields, so it will look much more beautiful, actually. So let's dive into getPairDevices internal, which is actually the implementation of the callback getPairDevices. The fifth argument is data that is absolutely controlled by our input. So I'll give you a moment, just if you're seeing anything, I'll refresh a little. So if you were quick enough to notice it, there is something unusual here. The fifth argument is controlled by us. Then what Apple tried to do here was to reference the first variable on the stack, documenting from it data that is absolutely controlled by us from our Sandbox application, and then they're assigning it to a new pointer on new variable on the stack. So I thought about it a little, and what I had in mind was that Apple just tried to initialize a dynamic array on the stack. But what is the problem with it? Let's see. They are going to take the fifth argument, which is W4. They're going to do some calculation, put it in X9, and they're going to take the stack pointer, put it in X8. But eventually, they're going to put all of this calculation back to the stack pointer. So it's pretty weird because it's not weird. It's just they are trying to allocate new memory on the stack. But what they failed to do was to check how much memory I'm allocating. So they acknowledge this bug with the CV 4095, which is basically a relative control over the stack pointer, which could lead to info leak inside of the internal functions. And this bug exists in 6 different callbacks they had. So how they fixed it? They decided to fix it by checking how much memory I'm trying to allocate on the stack. So this was the first bug I found in Blue2D. I just saw that I think someone didn't really thought about why they are doing it correctly. This is not something you should do in your code, allocating on the stack without checking the length of how much you're trying to allocate. So let's understand how that Bluetooth session actually works. Blue2D will hold all of the attached clients. Attached clients are Bluetooth sessions. You have daemons, the clients can be daemons, can be applications, and whenever, let's see how I'm lasering, okay. And whenever a daemon wishes to attach to Blue2D and start to use Blue2D capabilities, it is going to call the API called BTSessionAttach, and is going to hold some information of the session, and will ask Blue2D to hold that information. As part of the initialization process, SharingD is also going to send the API called bt local device add callbacks, which was a little bit weird to me. Why does sharing D needs to add callbacks on Blue2D side? I mean, something was weird here, but basically what I had in mind was that callbacks is always a really good thing you should start looking for, because it's holding addresses. Let's see what can I do here. So what I decided to do was to dive into the Bluetooth BT local device add callbacks process. And I found the callback actually it's the message ID 3. This is the function that handles the BT local device add callback under Blue2D. And the add callbacks internal, which is the actual implementation of the callback, is getting 3 different parameters. One is the session, the second one is the callback address, and the third one is the data. So let's think about it for a moment. What we saw on mediaserverd, if you remember, they didn't really use any session token. They identified the session to mediaserverd by the local port. But now they're using some kind of session. This data is controlled by us from our Sandbox application. The second one is the callback. Why they are sending some address to Blue2D? That is also weird. So let's see. Basically, what they're doing on Blue2D is taking that session token and verifying it against dictionary of all the attached token. And if it can't find the session, it is going to return 7, which means error, I could not find the session. Okay, so I thought about it for a moment. Actually, I just tried to play with it a little, but then it came to my mind, what if I am a malicious application and I will repeatedly try to send BT local device add callbacks and to brute force that session token? Again, I don't know what is the size of that field, but let's think about it. Theoretically, if I will be able to, from my Sandbox application, to brute force that session token and eventually bypass the check, I will be able to add callbacks to sharing D eventually. And if there is going to be an event, sharing D will just go to address that was controlled by me with the data. So the next slide is actually really funny, because all it takes is just doing this, is to make a for loop, increment from 0 to 2 bytes, and doing some bitwise operation to order it, and to try to add new callback to that bit with the data 1337. And what it actually was supposed to do is that I found out that the session token was only 2 bytes. And basically what it means that if this is working, this was a moment before I executed it, if it's working, I will be able to add new callbacks to all of the clients of Blue2D. So I just executed it from a Sandbox application, of course, and it actually crashed my old device. All of the demons were just crashing and jumping to address that was fully controlled by me. Each one of the demons that are using Blue2D, which here is just, I think, a short list. I think there are even more. And I also can control over one of the registers for exploit. In order to exploit it, of course, there is some work to do. But basically, this is a really good start to exploit those demons. So Apple decided to fix it. They acknowledged the bug, of course, and they decided to fix it. And their fix is pretty simple, and on first sight, it sounds pretty decent one. And they decided to use some global variable, that is sender ID, and this is being generated when they are initializing the Bluetooth session. And that token is initialized using arg for random, which is 32 bits, 4 bytes. So they decided to change the token from 2 bytes to 4 bytes. To any of you that is familiar, brute forcing 2 bytes and 4 bytes, it's the same. So they kept the bug. It was allegedly fixed on 11.2.5, and the bug is actually still exists in 11.4. So to a question I got a lot on Twitter when there is going to be a jailbreak. So I didn't publish any, but on the last DEF CON, a guy named Spark from Alibaba, I think, yes, claimed to fully exploit that bug using another primitive he had. And actually, he made a private jailbreak out of it. So, what did we have here? My main goal was to find a Sandbox Escape in order to widen as much as possible my attack surface. And what I found is that I could control all of the daemons that actually made my attack surface just huge to the kernel. So basically that is it. Some references I think worth mentioning, JTool and some other tools I used. You can find fully more detailed POC under my GitHub. You can find the Spark blog post on this presentation on the last 2 links. I think it was reading. And some credits, of course, to Zimperium for my paycheck, and Jonathan Levine for making a lot of references, few of my colleagues, Adam, Tamir, and Nikias, and of course to Spark for semi-publishing the exploit for this vulnerability. Basically, that is it. Thank you for hearing me out. And
thank you very much, Rani. Are there any further questions from the room, perhaps? Yep.
A nice talk. So my question is, when you said that you were communicating with mediaserverd or other daemons using mach messages, did you actually write this mach code in your app, or you used APIs which in turn used mach messages internally?
Okay, basically, it stopped working. Okay, it's working. Basically, when you want, mach messaging is a message that you're sending to the kernel, and the kernel will deliver it to the application. I mean, to the remote port, to where you want to send that message. So, was it what you were asking, or?
So you can basically write all the code in mach, like theoretically, right?
Sorry?
You can write the whole code in just mach messaging, everything.
Yes.
Because everything internally works using mach messaging.
Correct.
My question was for this expert, did you use APIs which internally called mach messages?
No,
or you wrote your own
directly mach messages.
Okay.
That was the idea. I know, because if I was going to use the VT decompression, essentially the coldframe API, the decode frame API was going to serialize that message. But I want to send directly those mach messages to the daemon, so I could fuzz it, because I want to fuzz the serialization process.
Any other questions?
Thank you.
Thank you very much, Rani. Thank you very much, Rani.